Weng Chun. Now I'm going to present my part, which is nozzle and diffuser. Okay. Nozzle and diffuser are commonly utilized in jet engine, in rocket, in spacecraft, and in garden hoses as well. Okay. First, we're moving on to nozzle. Nozzle, the cross-sectional area of the nozzle is decreasing from the inlet to outlet. And due to this decreasing of cross-sectional area, it will cause the velocity to increase while the pressure to decrease. And there's a very important point is there's no heat transfer in nozzle as it is an insulator. Okay. Due to it, there is no heat transfer and there's no work done as well. Okay. The shape of diffuser is totally opposite to the nozzle due to the cross-sectional area of the diffuser is increasing from the inlet to outlet, and this increasing of cross-sectional area will cause the velocity to decrease and cause the pressure to increase. And this is same with the nozzle due to there is no heat transfer in diffuser. Due to there's no heat transfer, Q equal to 0 and the work done is equal to 0 as well. Now we're moving on to a simple question. Air at 10% degrees Celsius and 80 kilopascal enters the diffuser of a jet engine steadily with the velocity of 200 meters per second, and the inlet area of the diffuser is 0.4 meters square. The air leaves the diffuser with the velocity that is very small compared to the inlet velocity. Now we have to determine the mass flow rate and the temperature of air leaving the diffuser. Before we moving on to the solution, we have to mark down the information and important keywords like 10% degrees Celsius as T1, P1 80 kilopascal, then the V1 equal to 200 meters per second, A1 equal to 0.4 meters square, and very important keyword is the velocity of outlet is very small compared to the velocity of inlet. Therefore, we can assume that the velocity outlet is equal to 0. Now we're moving on to our solution parts.
Based on the question, we can draw out the diffuser diagram for us to have a more easier understanding. Okay. After that, we can label down the information provided. Okay. P1 equal to 80 kilopascal, temperature 1, 10 degrees Celsius, area 0.4 meters square, velocity equal to 200 meters per second. Okay. The first question are asking us to find the mass flow rate. Okay. Mass flow rate. Before we get the mass flow rate, we have to find the value of specific volume. Based on the information provided, we can assume that there is an ideal gas. Therefore, we're using the ideal gas law. PV equal to RT, and the V here is specific volume. Okay, then we have the formula RT divided by P. Okay. RT will have 0.287 kilopascal meter cube per kilogram Kelvin. The temperature here we are using Kelvin in unit, therefore we need to add the 273 with 10 degrees Celsius, and we're using Kelvin in unit, and divided by 80 kilopascal. Okay, we're using the calculator. 0.287 283 divided by 80, and we get 1.015. Now we check out the unit. We can simplify the unit, kilopascal, Kelvin as well. Therefore, we left only meter cube per kilogram. After we get the value of specific volume, we can find out the value of mass flow rate, which is 1 over specific volume multiply with velocity and area. 1 over 1.015 multiply 200 multiply 0.4. Multiply 200 multiply 0.4. We get 78 78.8. 78.8. Okay, if you're not sure with the answer, we can check with the unit. Okay, 1 over specific volume, which is kilogram per meter cube, multiply with meter per second, multiply with meter square, and simplify the unit, we get kilogram per second again. The unit is same with the mass flow rate. Okay. Therefore, we consider that this is the final answer for the value of mass flow rate. For the question B, we're asking to find the temperature of air leaving the diffuser, which is T2. Okay. As we know that the rate of change of energy flow is equal to 0 in the nozzle and diffuser. Based on the energy balance, we can say that the energy flow in, the rate of energy flow in is equal to rate of energy flow out. Energy, we have the formula of heat transfer plus work done plus internal energy, which is enthalpy change, changes kinetic energy and potential energy. Okay. Now we're using the formula mass flow rate multiplied by enthalpy plus velocity square divided by 2 plus gz. Z here is equal to height. The explanation in the previous slide, we able to know that there's no heat transfer, there's no work done in the nozzle and diffuser. And for this question, the height also same, therefore we can put it as 0 as well. Okay, now we can substitute the formula, this one, into this equation. Okay, now we can write out mass flow rate multiplied by enthalpy in plus velocity in square divided by 2 equal to mass flow rate enthalpy out plus velocity out square divided by 2. Okay, the enthalpy at the temperature 283 Kelvin is equal to 283.14 kilojoule per kilogram, and the velocity in is equal to 200 meter per second. Okay. Based on the question, they have mentioned that the velocity out is very small compared to velocity in. Therefore, we can assume that the velocity out is equal to 0. Okay, now we have all the information and we just substitute into the equation. Okay, first we can simplify the mass flow rate because they are same. Okay, 283.14 kilojoule per kilogram plus V in equals to 200 square divided by 2. Now we have to be careful with the unit because we already changed into meter square per second square. Now we're gonna change this to kilojoule per kilogram. So we divided by 1000 meter square per second square is equal to enthalpy out. Because here the velocity out is already equal to 0, so therefore we no need to write it. Okay, now the enthalpy out value we can get by using calculator. Okay, 283.14 plus 200 square divided by 2 multiply 1 over 1000. You get 303.14 kilojoule per kilogram. Now the enthalpy is equal to 300. Enthalpy out is equal to 303.14 kilojoule per kilogram. Now we can, according to the table 17, we can find the temperature, which is the temperature is equal to 303 Kelvin. Kelvin in unit, yeah. Okay, this is the final answer. For the other device, I would like to pass it to my other members.
Good evening, Doctor. My name is Ong Wei Cean from Section 3, metric number AD190281. So today I would like to talk about topic of turbine. A turbine is basically a mechanical device that extracts energy from a fluid flow and imparts the energy to the blades of the turbine, and lastly convert it into mechanical energy. In this diagram, this is the simple diagram for turbine. We have fluid coming into the turbine, and the fluid rotates the blade of the turbine, which is coupled to the shaft. Lastly, the fluid comes out. Basically, turbine is an energy producing device, whereas compressor and pump are energy consuming devices. Turbines are classified into three parts, which is type of working fluid, direction of fluid flow, and fluid action. So if you have steam come in and go out, then that kind of turbine is steam turbine. Let's say water come in and go out, which is hydraulic turbine. You also can have certain gases which come in and go out, which is gas turbine. The next classification is direction of fluid flow. The fluid flows in particular directions also create two kinds of turbines. The first is an axial flow turbine, where the fluid is flowing to the axis of the shaft. The second is radial flow turbine, where the fluid runs around a shaft. The third classification is based on the fluid action. The first action is pressure compounding. The second is velocity compounding, and then lastly is the pressure velocity compounding. Let us look at some example. The power output of an adiabatic steam turbine is 5 MW, and the inlet and the exit condition of the steam are as indicated in figure 5.31. We are required to compare the magnitudes of delta H, delta KE, and delta PE. B, determine the work done per unit mass of the steam flowing through the turbine. So we can see that the inlet and exit conditions of a steam turbine and its power output are given. We assume that this is a steady flow process since there is no change with time at any point. The system is adiabatic and thus there is no heat transfer. So A, at the inlet, steam is in a superheated vapor state and its enthalpy is, since P1 equals 2 megapascal, T1 equals 400 degrees Celsius, therefore H1 equals 3248.4 kilojoule per kilogram. We can get this value from table A6, which is pressure equals 2 megapascal, and then saturated temperature equals 400. So it's 3248.4. So at the turbine exit, we obviously have a saturated liquid vapor mixture at 15 kilopascal pressure. The enthalpy at this state is H2 equals HF plus S2 HFG equals HF equals this one, 225.94, and then HFG equals 2372.3. So HF plus S2 is given 0.9 times 2372.3 kilojoule per kilogram equals 2361.01 kilojoule per kilogram. Then we find the difference between H2 and H1. Delta H equals H2 minus H1 equals 2361.91 minus 3248.4 kilojoule per kilogram equals negative 887.39 kilojoule per kilogram. And then the delta KE equals V2 squared minus V1 squared over 2 equals V2 is 180 and then V1 is 50. 180 squared minus 50 squared over 2 equals 14.95 kilojoule per kilogram. And then potential energy equals G bracket Z2 minus Z1 equals G equals 9 gravity force 9.81 and then times Z2 is 6 and then Z1 is 10 negative 4 and then times and then you get negative 0.04 kilojoule per kilogram. And then for B, determine the work done per unit mass of the steam flowing through the turbine. The energy balance for this steady flow system can be expressed in the rate form as rate of net energy transfer by heat, work and mass equals rate of change in internal kinetic and potential energy. So E dot in minus E dot out equals dE over dt. Since this one is 0 because both are equal, and then E in equals E out. So E in is 4m H1 plus in is 1. H1 plus V1 over V1 power 2 over 2 plus GZ1 equals W out plus M H2 plus V2 power 2 over 2 plus GZ2. So and then dividing by the mass flow rate M. So we divide this equation with mass. So we cancel off mass and then the work done by the turbine per unit mass of the steam is determined to be W out equals negative H2 minus H1 plus V2 squared minus V1 squared over 2 plus GZ2 minus GZ1. So all this value we already obtained in the question A, which is H2 minus H1 is negative 887.93 and then kinetic energy 14.95, potential energy negative 0.04. So we sub in those numbers in these unknowns and then lastly we get 872.48 kilojoule per kilogram. So that's all I want to say. Thank you.
My name is Choong Jun Jie. I am from section 3. My group name is ATS Thermo. My metric number is AD190205. Today I want to present a subtopic of my group assignment, which is compressor. Let me give some introduction to the compressor. Compressor is a device used to increase the pressure of fluid. Work is applied to the compressor from an external source through a rotating shaft. Therefore, compressor involved in work input. Compressor is capable of compressing the gas to a very high pressure fluid. Now we see one example of the question of compressing air by a compressor. Let's see the question. Air at 100 kPa and 280 Kelvin is compressed steadily to 600 kilopascal and 400 Kelvin. The mass flow rate of the A is 0.02 kg per second and a heat loss of 16 kJ per kilogram occurs. During the process, assuming the change in kinetic and potential energies are negligible, determine the necessary power input to the compressor. So in this question, we need to find the power input for the compressor, and we assume that the change of kinetic energy and potential energy are negligible. Now we see the solution. This is how I start my solution. Since the rate of energy transfer by heat, work, and mass is equal to the rate of change in external kinetic and potential energy. Thus, the energy input minus the energy output will equal to the rate of change in the system. Since we assuming the system is a steady flow system, so the rate of change in the system equal to 0. The energy input minus the energy output equal to 0. So we will get the energy input equal energy output. And we know the change of kinetic energy is equal to the change of potential energy. So we will get the equation power input plus the mass flow rate times enthalpy 1 equal to the rate of heat transfer plus mass flow rate times enthalpy 2. And we can rearrange the equation and get the formula power input equal to the mass flow rate times heat loss plus mass flow rate times enthalpy 2 minus enthalpy 1. And how we get the enthalpy 1 and enthalpy 2? For the question, that is given a kilopascal and Kelvin, but in ideal case, will depends on temperature only. So we will just look at the temperature. We can get the value from table A17. For the enthalpy 1, which is at 280 Kelvin, we get the value from the table A17 is 218.13 kJ per kilogram. For the enthalpy 2 at 400 Kelvin, we get 400.98 kJ per kilogram. Okay, so now we substitute the value into the equation we get just now. The power input equal to 0.02 kg per second times 16 kJ per kilogram plus 0.02 kg per second times 400.98 minus 218.13 kJ per kilogram. So we will get the power input, which is 2.74 kilowatt. This is all of me. Thank you.
Hey everyone, selamat sejahtera. My name is Chang with matrix number 190217 and from section 3. Today I'm going to present about the tutoring valves. So let's begin. What is tutoring valves? The tutoring valves are any kind of flow restricting devices that cause a significant pressure drop in the fluid. So here's some examples of the tutoring valves. The first one is an adjustable valve. Second one, a false plug or a simple capillary tube can be our tutoring valves. So what is the difference between a turbine and a tutoring valves? So unlike turbines, tutoring valves produce a pressure drop without involving any work. so there's no work done throughout the process. Then the pressure drop in the fluid is often accompanied by a large drop in temperatures. So because it's drop temperature through the process, and for that reason, the throttling devices are commonly used in refrigeration and air conditioning applications. And the throttling valves are usually small devices, and the flow through them may be assumed to be adiabatic. The Q equal to 0 since there is neither sufficient time nor large enough area for any effective heat transfer to take place. Also, there's no work done. The W equal to 0 and the change in potential energy, if any, is very small. The change of PE equal to 0 in through axis. Velocity is often considerably higher than the inlet velocity. In many cases, the increase in kinetic energy is insignificant, that the K equal to 0. Then, from these assumptions, that expects the conservation of energy equations for this single stream steady flow device are reduced to the H2 nearly equal to H1. So we can assume the enthalpy doesn't change throughout the process. So we can better understand through these energy balance equations that the internal energy and the flow energy is equal to constant, that the U1 plus P1 V1 equal to U2 plus P2 V2. The final outcome of the throttling process depends on the two quantity increased during the process. So if the flow energy increased during the process, so the internal energy will decrease. This one increase, this one decrease. So the decrease in internal energy will accompany with a drop in temperatures. So if the PV, the flow energy decreases, the internal energy and the temperature of the fluid will increase during the throttling process. So that's what we can get from these equations. So let's look at for the ideal gas situations, the H equal to HT, thus the temperature has to remain constant during the throttling process. So for the ideal gas, the temperature of the ideal gas does not change throughout the whole throttling process. So we can look through this, the T2 equal to T1 and the H2 equal to T1. Since that the H equal to HT, H is a constant, so the temperature doesn't change for ideal gas. So for the better understanding for this, we look at these examples, the expansions of refrigerant 134A in a refrigerator. So here say the refrigerant 134A enter the capillary tube of a refrigerator as a saturated liquid at 0.8 megapascal and is throttled to a pressure of 0.12 megapascal. So what we have to do is determine the quality of the refrigerant at the final state and the temperature drop during this process. So the temperature difference and the quality, the final state of the refrigerant. So now we try to analyze these equations. So we said the enters at 0.8 megapascal and it is throttled out, so it exceeds at 0.12 megapascal. So we got our P1 and P2, and the question says it's entered the state. The fluid entered the capillary tube as a saturated liquid, so we can know this is the initial state. And before the solutions, we make some assumptions for the equations of these regimes. So the first one, the heat transfer from the tube is negligible, and the kinetic energy change for the refrigerant is negligible, so we neglect these things. And from the equations, we know the flow through capillary tubes process is a throttling process, so we also can get that the enthalpy of the refrigerants remain constant, which the H2 will equal to the H1. And Now look at the solutions. So we get the Pascal P1 equal to 0.8 megapascal. So from this, we can get the temperature and the enthalpy from the table A12. So from the A12, 0.8 megapascal equal to 800 kilopascal. The temperature is 31.31, and for the enthalpy is 95.47. So at acid, the P2 is equal to 120 kilopascal. So we can get the temperatures, the enthalpy for the saturated liquids and saturated vapor is 236.97 and 22.49. So here is the Q. So from this data, we can see that the HF is smaller than the H2, which is equal to H1, H2 to the H1, and the HG is the largest. So from this, we can show that the refrigerant exists as a saturated mixture at the acid step. So after the throttling process, the refrigerant is the saturated mixture. So how we get the quality of the refrigerants is we use H2 minus HF and divide by HFG. So by these equations, we get our H2 H1 95.47 minus 22.49 HF, and HFG is equal to our Hg minus HF. So it's 236.97 minus 22.49. So we get our quality is 0.340, and since the acid step is the saturated mixture at the 0.12 megapascal, the acid temperatures must be the saturation temperature at these pressures, which is negative 22.32 degrees Celsius. So the temperature change through the process is T2 minus T1. So it's this one minus this one. So we can get a temperature difference of negative 53.63 degrees Celsius. So from this, we know from the process, the temperatures is decreased by 53.63, and the 34% of the refrigerants is vaporized during the throttling process, and the energy needed to vaporize the refrigerants is absorbed from the refrigerant itself. So we got the quality and the temperature difference. So here is how we solve the questions. Okay, thank you everyone. And
Hey guys, my name is Jia Qing, matrix number AD190230. I am one of the group member of ATS Thermo, and this video is done as a part of my assignment of the course Thermodynamic. Today, I will talk about what is a heat exchanger. So theoretically, a heat exchanger is a device used to transfer thermal energy between two or more fluids which are at different temperatures. In more cases, the fluids can exchange heat without direct contact. So the diagram above is what a common heat exchanger look like. So let's talk about how it functions. In the diagram below, fluid 1 is at a low temperature and fluid 2 is at a higher temperature when it go into the heat exchanger. The heat transfer occur from fluid 2 to fluid 1, so when they come out, the fluid 1 has increased in the temperature and fluid 2 will decrease the temperature. So heat exchanger has widely used in many applications, many products, so such as area heating, air conditioning, which is just like this, chemical processing, or waste heat recovery, which is like this. It's not common to see the second diagram. Only we can see in a large industrial area. After the introduction, let's talk about how to solve the question of heat exchanger. There's many things can be asked in the question, such as the mass flow rate of fluid, temperature of fluid, and many more. So this time I will explain how to solve a mass flow rate question. So the question asks, a concentric countercurrent heat exchanger is used to cool lubricating oil. Water is used as the coolant. The inlet and outlet temperature are given in the table. The oil have the inlet temperature of 100 degrees Celsius, outlet temperature of 55 degrees Celsius, and water has 35 degrees Celsius as the inlet temperature. Outlet temperature is 42 degrees Celsius. The mass flow rate of oil is given as 0.1 kg per second. So what is the mass flow rate of water needed to maintain these operating conditions? So this question is actually very simple. All you have to use is an equation of the rate of heat transfer, which is equal to mass flow rate times the constant of specific heat times the delta T, which is the difference between two temperatures. So theoretically, the rate of heat transfer of oil is equal to the water, so we can get the second equation, which is written below. And beside that, the constant specific heat of oil and water are also given. For oil is 2131 joules per kilograms degree Celsius. For water is 4178 joules per kilogram degree Celsius. So since we know all the data, we just have to make a simple max equations, and finally we can get the mass flow rate of water, which is 0.33 kg per second. So below that is the calculation of the rate of heat transfer. I think some of you are curious about why there's difference between the rate of heat transfer of oil and the water. It's because the mass flow rate of water used is a carry digit. So if we use the original one, we will get the same value as the oil, which is 9590 joules per second. So that's all for me. Thank you.